Welcome to qnawire.
For this problem, we will use the expression for Coriolis acceleration that we derived in problem 60 part B, where we got the Coriolis acceleration to be equal to twice of velocity times omega. Now if you uh, get more specific, this expression can be modified to twice of v perpendicular times omega. And v perpendicular in our case is v times cos lambda times omega, where lambda is given to be 44 degree. And v is the vertical speed of the ball. Now, the vertical speed v is not constant as the ball falls, and therefore we can use kinematic equation now, since the acceleration is constant and is equal to gravity. We can use this kinematic equation. So we get from here that v is equal to v naught plus gt. Now assuming the ball starts from rest, therefore v naught goes to 0 and we get v to be equal to g times t. We can substitute this expression of v into this equation and we get the acceleration, the Coriolis acceleration, to be equal to twice of gt cos lambda times w. Let me write it in a nicer way. Yeah. Now this is not a constant acceleration because time is changing, and therefore to find the deflection due to this acceleration, we must integrate twice to get the distance. What I mean is, first we have to find the velocity, which goes like integration of the Coriolis acceleration. So that will give us the Coriolis velocity. And then we have to integrate the velocity one more time to get x Coriolis. So let's do that right now. So we have a Coriolis to be equal to 2 omega g cos lambda. Since this part is a constant, we can take it out of the integration. So this will then be equal to, assuming we are integrating from 0 to t, and the initial velocity of, well, the initial velocity is 0, therefore this will just be equal to v Coriolis, which is the final velocity, final Coriolis velocity. So now we can integrate this factor and we get the expression to be t square over 2, and this is equal to cos lambda. Now we use this expression to integrate again to find x Coriolis, or the Coriolis deflection. So again, this part is a constant, so we can take this out of the integral expression and we integrate it from 0 to t, and we assume that the initial deflection is 0. So let's say we are integrating from 0 to the final Coriolis deflection. So this will then give x Coriolis to be equal to, the integral of this is t to the power 3 over 3. So we can write this as omega g t cube over 3 times cos lambda. Now to find a value for the Coriolis deflection, we need t, which is the time of flight. Now the vertical motion is just uniform acceleration for an object dropped from rest. So we can solve the kinematic equation for the vertical motion to get an expression for the total time of flight. So this is the expression that we will use right now. And since the initial velocity is 0, so this term goes away. And y minus y naught is just the distance covered in the vertical motion. So this is the height the ball goes. Now we can get time, which is equal to root over of 2h over g. Now we will use this expression of time and plug it over here to find the Coriolis deflection. So let me just write that expression again. So this is what we got. Now we will use this time into this equation. So we have now we can simplify this equation a little bit. So we take the cube root and then we take the cube and then take the square root. So finally you'll arrive at so this step is not necessary. So you can skip this step and just plug the values of h and lambda that we have. But yeah, I'm gonna just go simplify this expression, but otherwise you can also use this expression that will just work out fine as well. Now let's plug the values of omega. So omega is 2 pi radian in 1 month, which is 86400 seconds. So let me just check if it's 1 month or 1 day. So yeah, so we have this is basically equal to 1 day. So now we can, so this is omega. Now we will plug the value of lambda to find cosine lambda. So that is equal to cosine of 44 degree. Now we have 8h cube over g. So h is given to be 110 meters and g is 9.8 meter per second square. And we solve this and we get the Coriolis deflection to be 0.018 meter. Therefore, the ball is deflected by about 2 cm in falling 110 meters. So, yeah, one more thing that I want to mention is if you are worrying about how to get omega, remember that the Earth covers one full rotation in 24 hours. So we have 2 pi radian in 1 day. And if you do the calculation, 1 day is 24 hours, 60 minutes, and 60 seconds. which is in fact equal to 24 times 12 times 100, and this is equal to 864. So you have this much, this many seconds in one day, and that's what we did over here.